Let's take a look at simple harmonic motion and damped motion. First, let's just talk about simple harmonic. If you could envision, we're in this vacuum. So, no friction, no gravity, nothing. We have this spring in this vacuum, okay, and there it is sitting at resting point, right? We could pull the spring down to here, and if we let it go, it would go past that resting point. It would go beyond it. Then it would come back past that resting point, extend, come back past the resting point. And what you'll notice here is that the behavior of this, is sinusoidal, okay? Sine function or cosine function. So that's the first thing we're going to look at. When something is simple harmonic, no outside forces that are damping this spring. Or maybe there'll be a pendulum swinging back and forth, right? So we're pretending it's in a vacuum, and basically there's no external forces slowing this down and damping the motion of the spring or the swinging of the pendulum. Okay, so there's nothing there to slow it down. Well, if that's the case, then we're looking at either a cosine function or a sine function of such. We already know how to form equations with sine and cosine. We already know that A is the amplitude. We already know that the period, the time it takes to do one full cycle, is 2 pi over, in this case, we're using omega, which is the variable in front of it will be a number, but it's the variable that they're using here in front of our input of time, okay? Frequency, now what is frequency? Period is the time it takes to do one oscillation. Frequency is the amount of oscillation we can fit in to 1 unit of time. So you will notice here that the period and the frequency are reciprocals of each other. Okay, let's take a look, put this stuff in action. All right, first problem here. We have these functions. Let's find the maximum displacement, find the period, which is the time for one full oscillation, and then the frequency, which is the amount of oscillation we can get into 1 unit of time, and then do a small sketch. Okay, so that's what we're going to do for these first ones here. I'm going to go back up to this previous image here. I didn't tell you how high it went or how low it went, but we already know that this value is from the midline, the A, and same thing here. Okay, so now if we think about it in terms of the word displacement, we're going to say displacement is the distance it goes from its resting position. Well, if you're looking at this as its resting position, then the distance that it goes, the maximum distance it goes from its resting position is A. So that is the maximum displacement, okay? So for this first example here, our max displacement is 5 units, okay? The period, which is the time it takes to go 1 full oscillation, well, normally for sine it's 2 pi, and we're dividing it by omega. So in other words, it takes 2/3 pi to do 1 full oscillation. Now, the midline, there's no plus on the end. We've already seen equations of sine early, chapter 7, right? We graphed, wasn't even chapter 7. Go back to 6. Is we graphed sine functions and cosine functions already. So we know a sine function. Come on, let me draw a sine function. We know goes through the origin, okay? And what we're saying is this sine function hits a max height of 5, a min height of -5, and it does all of it looking like the sine curve. In 2/3 pi. So that means this mark would be 1/3 pi, and we could certainly break it down more. So there is 1 period worth. Okay, so we have my sketch. Let's see. frequency. We didn't answer a frequency question yet. So when the period is 2/3 pi, or in other words, 2 pi over 3, this is time per oscillation, right? Frequency is the amount of oscillation per unit of time. So in other words, we would reciprocate it. Now, sometimes it's easier to think of this not as 3 over 2 pi, but if we grab our calculator, searching for mine here, 3 divided by 2 pi will equal, it's roughly a half, right? 0.477, and this is the amount of oscillations that happens in one, and it's not giving us the time, like is it seconds or minutes, but let's just say 1 second, okay? All right, so that's the first one. Let's look at the second one now. 6 cosine of pi t. All right, so I know the max displacement is 6. I know that the period is 2 pi divided by pi. So in other words, the period is 2. They didn't give us the time, whether it was seconds or minutes. I'm going to say it's seconds. So we're going to say it's 2 seconds per oscillation. So that means that the frequency is reciprocated, 1/2 of an oscillation per 1 second. So there's my displacement, my period, my frequency. Well, we know that the cosine function starts high, ends high, and it's going to do all of it. Max is 6, min is -6. And it does all of it in 2 seconds. That means in 1 second time, it has gone 1/2 of the cycle, which we can see. Okay, next one, another cosine function. Here, I can see that the max displacement is 5. The period is 2 pi divided by pi over 2. Well, that's 4 seconds per oscillation, which means that the frequency then is 1/4 of the oscillation happens for every second. Okay, so displacement, period, frequency. And then to graph this, 5, -5, those are how high and low it will go. This is a cosine function, so starts high, restarts high, and that's happening at 4 seconds, which means this is 2, means this is 1, and this is 3. So that means 1/4, you can probably visualize it here, 1/4 of the oscillation happened in 1 second. All right, let's keep moving here, looking at other examples. An object is pulled down on a coiled spring 2 inches and then released. 1 oscillation is 1 second. Develop a model for the displacement d of the object from rest after t seconds. Okay, so they say assume no friction. That's them saying, hey, this is going to be a simple harmonic equation. Okay, so basically just like what we just had, but we're doing the problem in reverse. They're explaining it. Our job is to find the equation for it. All right, so here's what we know. The period, which we know is calculated 2 pi divided by omega, is, they're telling us 1 second big. So if we solve this, omega is equal to 2 pi. Now, just to do a sketch of this, they're telling us that the object is pulled down and then released. So it's starting down here, 2 units below, and then it is released. So that means there's 1, and it took 1 second to do that. 1 second, and it did the full oscillation. Okay, this is a cosine function, So think back about when we learned about cosine functions. This cosine function is starting at the lowest point, not the highest point. So up here in the front of it, the a value is going to be a negative. So it's been reflected over that axis. Okay, I know omega is 2 pi, and that's in front of the variable t. There's my equation for the displacement at time t. All right. Number 3, consider this displacement function. Describe the motion. Well, you haven't seen a damped equation yet, so it's simple harmonic. But if you look on the bottom of the screen here, this is how we're going to represent damped motion. Now, this is when we do have factors in place, gravity. Maybe if there's a bobber at the end of the spring, there's a certain mass to that, right? So there's impacts, maybe the density of the air. Like there's all these things that could affect the rate at which the item kind of slows down, right? So you'll notice these equations, when it is damped, have a bit more going on in them. Specifically, this part right here. Okay, now different books will describe that piece differently. My previous textbook that I use with my courses, they had C broken down with involving mass. We're not going to do that for this particular book that I work with. It's just that there's a damping factor. There's a lot that goes into that damping factor, and we're going to say it's the value of C. Okay. If you keep taking courses and say take a physics course, you'll dive deeper into what C is. Okay. All right. So because for number 3, we don't have that extra piece involved, notice there's a variable, right? Because we don't have that here for number 3, this is simple harmonic. Okay. What's the maximum displacement? Well, we know that that's the A value, so this is 10 units. Okay. What is the time required for one oscillation? Well, we know that that is period, and it is calculated by 2 pi divided by omega, which in this case is a 3. Okay, so this is seconds per oscillation. And when they want frequency, they're asking for how much of an oscillation per 1 second. And we certainly could find the decimal approximation. And honestly, that's very similar to the first example that we did. So, okay, now let's talk damped. Damped, there's a little bit more to it, right? We have this extra piece here. And if you considered your spring now, forces would make it past the midline. If you pulled it down and let it go, it would go here. And even then it would come back down past the midline, but it wouldn't probably go down as far as it did originally. Why? Because there's tension in the spring, right? How tight is it coiled? There's all these things that are at play, bringing it to approach the midline, right? Displacement is the max displacement is changing every single time a new cycle or a new period is happening. So, all right. Or if you think of a pendulum swinging, that has the same effect. Ultimately, it's going towards its rest position. All right. Model the equation that fits these two scenarios and graph them with technology. Two mass spring systems exhibit damped motion at a frequency of 0.5 cycles per second. That means that both of them have the same frequency. Okay? If frequency is 0.5 cycles per second, then doesn't that mean that the period is, if you reciprocate that, 2 seconds per cycle? Okay. Both have an initial displacement of 10. Now, formula, A displacement for the first period. It's the maximum displacement, or the, in this case, initial displacement. Okay. Now, they both have an initial displacement of positive 10, so I'm going to say that the spring is pushed up and then let go rather than pulled down. The first has a damping factor of 0.5. The second one has a damping factor of 0.1. So if we look at these equations again, that's the C is the damping factor, right? So now we need to decide, do we have ourselves a sine function or a cosine function, right? It's not overly clear, but the fact that they're telling us the initial displacement, we're going to assume that that's the initial placement. Okay, so what do I mean by that? What I mean by that is, let's go with the first one. So first one, I know it says use your graphing calculator to graph it, but see if this makes sense to you. The first one has an initial position 10 units up, okay? And when the spring is released, it's going to bob down past the midline, right? But not go as far as negative 10. Okay? What you saw above, those two pinks are just kind of like a guide, right? So that means it's just to help you draw, like it's going to go down, but not quite as far. Then it's going to come back, not go as far. Does that make sense? Okay. Now, because they're giving us a couple different damping factors, how is that going to affect this image? And I'm going to use my calculator to show you that. So let's generate our two equations. Let's go displacement for the first one. We have a 10, and then we have an e to the our c value, which is, because when I showed you it was starting high here, I'm going to use the cosine function, okay? So negative 0.5t cosine omega. Omega, let's see here. I need to find that. I don't have that yet. If the period is 2, two pi divided by omega is equal to period of 2, which means omega is pi. Okay. Now that's for the first one. The second one has a different C value, and then structurally everything else is the same. Okay. So we are going to graph these. I need to and now we graph. Window, let's start that at 0. And now graph. There we go. We can clearly see. Now the red is damping, right? If we bring that X out more, we can clearly see that the red is damping. It's just that the blue is damping faster. Okay. All right, let's go back. Excuse me, find and graph the damped function using sine with the given information. 7e to the negative 10t times sine of, we'll have to find the omega that goes in front of t. So if the period is pi over 6, and that is calculated by doing 2 pi divided by omega, then I can see that omega is going to equal 12. So there's a 12 there. Okay. And we'll graph it, but we might as well graph both of these at the same time. So let's do that for the second one as well. My A, number in front, E, and then negative damping factor, T, sine, and now this is frequency. Now, frequency is 1 over period, right? So that means that my period is 1/20th, which means 2 pi divided by omega equals 1 over 20th. Wow. 40 pi is equal to omega. All right, let's graph again. All right. Oh, goodness. We got to change our window to see that red. It's damping extremely slow. All right. That concludes this section.